Welcome to section 4.3. Let's talk about partial derivatives. Now, if we have a function of one variable, y equals f of x, we can visualize the graph as a curve, and the derivative is the slope of the tangent line at any point. Now, if we have a surface, so a function z equals f of xy, then we've got a whole tangent plane at any point. And so what we do is we hold one variable constant. Now that has the effect of intersecting the surface with a plane, and then that does form a curve, and we can talk about the slope of that curve at any point. And that's the geometric interpretation of a partial derivative. Now here are the two limit definitions of partial derivatives, and you can see the partial derivative sign is a curly D. It's called a del. Okay, finding partial derivative using the limit definition of this function here, I did that on the next page, and you can read through that computation. And I found the partial derivative at a point 2, 1, and I got 4. So let's look at that, what that is geometrically. If we look at the point 2, 1, the partial derivative with respect to x, what we're doing is holding y constant at 1. So y equals 1, that's a plane, and we're intersecting the surface with that plane, and we get a curve, and right there is the point 2, 1, 5. The z-coordinate is 5 when x is 2 and y is 1, and the slope of this dotted line here that you see is 4. All right, is there an easier way to get partial derivatives? Of course there is. To find f(x), hold y constant, and to find f sub y, hold x constant. So I should mention that the partial del f del x can also be written as f sub x. Same thing with partial with respect to y. Okay, so let's find some partial derivatives. F sub x, we're going to hold y constant. So pretend y is just a number. So that's 2x plus 3y, because the derivative of x is 1. And then everything else is 0, because y is constant. F sub y is 3x plus 1, okay? Maybe you should pause the video and see if you can do the next one. All right, hopefully you did that. F sub x is 2xy cubed, because y cubed is a constant, that just carries along, plus, now, remember for the derivative of log, I'll give you the rule over here, d by dx of ln of a function of x, u of x, is u prime over u. So here we want on top the derivative of 3x plus y squared with respect to x. That's 3. And on the bottom we put 3x plus y squared. All right, and f sub y is 3y squared x squared plus, now we want the partial of 3x plus y squared with respect to y on top, which is 2y, and I put 3x plus y squared on the bottom. Okay, next one, I'm changing up notation. Find the partials again, so del z, del x. Here we need the product rule because we've got the product of two functions of x. So I'll take the derivative of the first, that's 4x cubed, multiply by the second, sine of xy cubed, and add on the first function, x to the fourth, times the derivative of the second. So the derivative of sine is cosine. We leave the argument alone, xy cubed, but then by the chain rule, we need to multiply by the derivative of the inside. The derivative of the inside with respect to x is y cubed. So let's clean that up just a little. 4x cubed sine of xy cubed plus x to the fourth y cubed cosine of xy cubed. Okay, now let's do the partial with respect to y. Del z del y is, I don't need the product rule. X to the fourth is constant, so I multiply by the derivative of sine xy cubed, which is cosine xy cubed, and now I multiply by the derivative of the inside, which is 3y squared x. So altogether, that's 3x to the fifth y squared cos xy cubed. Okay, and there's no reason to stop with two variables. We could find the partial of a function with respect to three variables. We just hold the other two variables fixed. So for example, if we want f sub z for this function f, we're going to hold x and y constant, okay? So f sub z would be, again, we're going to need the product rule. So 2z, and then multiply by e to the x, y, z plus y, and then add on z squared, and then we want the derivative of that exponential term. So we multiply by e to the x, y, z plus y, and then we have to multiply by the derivative of the exponent. The derivative of the exponent with respect to z is xy. So altogether, we have 2z e to the x, y, z plus y plus z squared xy e to the x, y, z plus y. Okay, here's a geometric question. The surface x squared plus y cubed intersects y equal -1 in a curve passing through this point. Find the slope of the tangent to that curve. So the question, we're being asked for a partial derivative at 2, -1. Do we want fx or fy? Well, if we're holding y constant, that means we want f sub x. So let's find f sub x. That's pretty easy. It's just 2x. So f sub x at 2, -1, plug 2 in for x, that we get 4. That's the slope of that line. Okay, higher order partials. We can do second order partials. We can do third order partials. So these are the notations for second order partials. There are 4 of them. And I'll just look at this one with you. The purple one, these are different notations for the same thing. And down here, I'll show you what I mean. So this bottom expression means take d by dy of del f del x. So you're going to do the partial with respect to x first, then the partial with respect to y. So you read that kind of backwards. Now the other one, this top box, means take the partial with respect to y of the partial with respect to x. So you read that forward. But again, they mean the same thing, just different notations. Okay, so let's find some second order partials. First, we need first order partials. So fx is cos y plus y e to the x. F sub y is negative x sine y plus e to the x. So pause and make sure you follow that. And then maybe try and find second order partials yourself. Okay, f sub x, x. That means take the partial with respect to x of f sub x. So the cos y will drop out because that's a constant. And then we just get so we get y e to the x. All right, f sub y, take the partial with respect to y of f sub y, and we get negative x cosine y, and that's it, because e to the x is constant, okay? F sub x, y. That means take the partial with respect to y of f sub x, all right? So that's negative sine y plus e to the x, okay? F sub yx, we take the partial with respect to x of f sub y. That gives us negative sine y plus e to the x. Notice that f sub xy is equal to f sub yx. That's not a coincidence, okay? Let's find some other second order partials. This is the function that we had on page 2, and we already found the first order partials, and I've just copied those down for us. And so now let's go ahead and find f sub x, x, okay? I want to think of this fraction here as just that expression with a negative exponent. So that'll be easier. I'm going to use the chain rule. So f sub xx is 2y cubed, and then I bring the minus down, I leave the inside fixed, subtract 1 from the exponent, and multiply by the derivative of the inside. So that's 2y cubed minus 9 over 3x plus y squared squared. Okay, f sub y, I can rewrite this like I did before, but it's really not going to help. I need to use the quotient rule, so I may as well use the quotient rule. Let me remind you of the quotient rule. F over g prime is f prime g minus f g prime over g squared. So f sub y is going to be 6x squared y plus, I'm going to have a big fraction. I want partial with respect to y of the top, which is 2, and then I multiply by the bottom, and then I subtract the top function, 2y, times the derivative of the bottom with respect to y, that would be 2y, over the denominator squared. Okay, let's clean that up. 6x squared y plus 6x minus 2y squared all over 3x plus y squared squared. Okay, and now let's find f sub xy. So we want the partial with respect to y of f sub x. So we're up here with f sub x. We want partial with respect to y. So that's going to be 6xy squared. And then I'll do some stuff in my head. I need to bring the minus down. So that's going to be a minus. And I'll end up with 6y over 3x plus y squared squared. Okay, I'm not going to find f sub yx because I know it's equal to f sub xy. Whoops. So this is equal to f sub yx by Clairaut's theorem that tells us that if you've got continuous, if everything's continuous and you're not in a nice open region, then partials are equal. Mixed partials are equal. And that generalizes, and I've got that explained right here. All right, I want to end with geometric interpretation of second order partials. So take a look at this function here. F equals x squared minus y squared. I've got a picture right here. Let's find f sub x. That's 2x. And notice that when x is positive, f sub x is positive, and f is an increasing function. We know positive derivative means increasing. So what I'm looking at is this curve here. Right there, you can see that as x increases, the values of the functions increase on that line. Now let's look at the second order partial. F sub xx is 2, and that's positive. And we know by the second derivative test, positive second derivative means concave up. And sure enough, that's a concave up curve. So that information about the second derivative works the same in 1 and 2 variables. Okay, and that is the end of this section.